There is something sitting at the center of our galaxy right now, about 27,000 light-years from where you are, that weighs 4 million times more than the Sunday. It is not a star. It is not a planet. It is not any kind of object that has a solid surface or a glowing face or any recognizable feature at all. It is a place where space itself has curved so completely inward that nothing, not matter, not dust, not even light, can escape. And for most of human history, we had no idea it was there. That object is called Sagittarius A star, and it is only one of perhaps 100 billion black holes estimated to exist across the observable universe. They are not rare. They are not exotic anomalies sitting at the edges of physics. They are everywhere. They are woven into the fabric of how galaxies form, how stars die, how matter organizes itself across cosmic timescales. And yet, for all of that ubiquity, they remain among the most genuinely mysterious things in the known universe. Tonight, we are going to settle into one of the most fascinating journeys physics has to offer. We are going to start with what a black hole actually is, move through how they are born, tour the strange architecture of their interior, and eventually arrive at questions that modern physics cannot yet fully answer. Questions about what happens to information when it disappears, about what the center of a black hole truly contains, and about whether there are things on the other side that we have no language to describe yet. The pace here is slow and deliberate. There is no rush. This is the kind of topic that deserves to be turned over gently, examined from multiple angles, and sat with for a long time, so get comfortable. Dim the lights if you like, and let's begin. Before we go any further, drop a comment and let me know where you're watching from and what time it is there. I love seeing where these videos travel, and if you haven't subscribed yet, now is a perfect time. There is so much more of this kind of deep, quiet science coming your way. Part 1. The Gravity of Nothing. The name black hole is, by any measure, one of the most evocative phrases in all of science. It conjures images of cosmic drain holes, of darkness so complete it becomes a presence in itself, of vast invisible mouths consuming everything within reach. But the name is also, in at least one important sense, slightly misleading. A black hole is not a hole in the way that a hole in the ground is a hole. It is not an absence of matter. It is an extraordinary concentration of it. The physicist John Archibald Wheeler is often credited with popularizing the term black hole in the late 1960s. Before that, these objects were called gravitationally completely collapsed stars, which is accurate but does not exactly roll off the tongue. The simpler name stuck, and it has shaped how people imagine these things ever since, sometimes helpfully, sometimes not. So let us spend a moment on what a black hole actually is, before we explore how it forms or what happens inside one. A black hole is a region of space in which the gravitational field is so intense that nothing can escape it. That is the core definition. Everything else follows from it. The reason gravity becomes this intense comes down to density. Gravity, in the way Einstein described it in his general theory of relativity, is not a force acting across empty space in the way Newton imagined. It is a curvature of space-time itself. Mass curves space-time the way a heavy object curves a stretched sheet of rubber. The more mass you compress into a small region, the more dramatic that curvature becomes. Now, here is the key insight. There is a specific threshold for every amount of mass. If you compress that mass below a certain critical radius, the curvature of space-time becomes so extreme that the escape velocity at that radius exceeds the speed of light. And since nothing in the physical universe can travel faster than light, nothing can escape. The region inside that critical radius is the black hole. The critical radius itself is called the Schwarzschild radius, named after the German physicist Karl Schwarzschild. Schwarzschild was a remarkable man with a remarkable story. In late 1915, while serving as an artillery officer for the German army on the Russian front during the First World War, he received a copy of Albert Einstein's newly published General Theory of Relativity in the mail. Schwarzschild read it carefully, understood it deeply, and within weeks had produced the first exact mathematical solution to Einstein's field equations. He did this from a trench in one of the most brutal conflicts in human history. He sent his solution back to Einstein, who presented it to the Prussian Academy of Sciences in January of 1916. Schwarzschild died a few months later from a disease contracted at the front. He never knew the full weight of what he had done. What Schwarzschild's solution described was the geometry of space-time around a perfectly spherical, non-rotating mass. And buried in that geometry was something that Einstein himself found unsettling, a radius at which the mathematics produced a singularity, a point where the equations produced infinities. For the Sun, that critical radius works out to about 3 kilometers. What that means is that if you could somehow compress the entire mass of the Sun into a sphere just 3 kilometers across, the resulting object would be a black hole. Its surface gravity would become so intense that not even light could leave. For the Earth, the Schwarzschild radius is about 9 millimeters, roughly the size of a marble. Compress the entire mass of the Earth into something smaller than a marble, and the same thing happens. The escape velocity at its surface would exceed the speed of light, and you would have a black hole. Of course, no natural process compresses the Earth into a marble, and no natural process compresses the Sun into a 3-kilometer ball, not under normal circumstances. But there are stars in the universe much more massive than the Sun, and for those stars, gravity is powerful enough to do exactly this. That is how most black holes are born. Which brings us to the next part of this story. But first, it is worth staying a moment longer with the concept of escape velocity, because it is the conceptual key to everything that follows. Escape velocity is the speed you need to reach to break free from a gravitational field. For Earth, that number is about 11.2 kilometers per second. If you throw an object upward at that speed from Earth's surface, it will keep traveling away forever, slowing down as it goes, but never quite stopping, never falling back. For the Sun, escape velocity from the surface is about 620 kilometers per second. Now imagine compressing the Sun's mass into a smaller and smaller volume. As the surface gets closer to the center, the gravitational field at the surface intensifies. The escape velocity climbs. At some point, the escape velocity hits 300,000 kilometers per second, the speed of light. From that moment, nothing can leave. The surface is not a physical barrier. There is no wall, no membrane you could touch. It is simply a geometric threshold in space-time, a boundary drawn by physics itself. We call it the event horizon. The event horizon is not the black hole. The event horizon is the edge of the black hole. The black hole includes the event horizon and everything inside it. And the word horizon is appropriate in an almost poetic way, because just as the visual horizon on Earth is a boundary beyond which you cannot see, the event horizon is a boundary beyond which we cannot receive any information. Any light, any signal, any particle that crosses inward never crosses back outward. The event horizon is a one-way door into a region of space from which, as far as our current physics tells us, there is no return. One of the genuinely strange features of the event horizon is that if you were falling into a large black hole, you would not feel anything special as you crossed it. There is no wall, no alarm, no change in the local physics of your experience. If the black hole is large enough, the tidal forces at the horizon are mild enough that you might cross the event horizon without even knowing it. From your perspective, you simply keep falling. The point of no return passes beneath you like an invisible line, and by the time you realize nothing looks any different, it is too late. You are inside, and you cannot get out. From the perspective of someone watching you fall in from far away, the situation is entirely different. Due to gravitational time dilation, which we will explore in detail later, time slows down dramatically near a black hole's event horizon. From outside, your fall appears to slow. You seem to redden as your light is stretched to longer wavelengths by the intense gravity. You appear to freeze just outside the horizon, becoming dimmer and more red, until you fade from view entirely. You never actually appear to cross it, from the outside observer's point of view, but from your own, you cross it in a finite time, and continue falling inward. Two perspectives, two completely different experiences, both of them real within their own reference frames. This is not a paradox. It is exactly what Einstein's theory predicts. Space-time near a black hole is so curved that distant observers and infalling observers are experiencing fundamentally different versions of events, which is either deeply satisfying or deeply unsettling, depending on your temperament, possibly both. The term black hole itself raises one more question worth addressing right at the start, which is whether a black hole is actually black. In the strictest sense, no. Not entirely. Stephen Hawking showed in 1974 that black holes are not perfectly black, but emit a faint form of radiation arising from quantum mechanical effects near the event horizon. This Hawking radiation means that black holes, over enormous spans of time, lose mass and eventually evaporate. For a stellar mass black hole, the evaporation time is so astronomically long that calling it practically infinite would be reasonable. We will explore Hawking radiation in detail later. For now, understand that the darkness of a black hole is real and overwhelming, but it is not perfectly absolute. Physics, as always, finds the nuance. What is entirely true is that a black hole emits no light of its own. It does not shine. It does not glow. The light we see in images of black holes, the brilliant glowing rings and accretion disks, is light from matter surrounding the black hole. The black hole itself sits at the center of that light, show as a profound absence, a circle of darkness against a blazing ring, a void so complete it becomes visible by contrast. That void, that darkness, against the fire of infalling matter, that is what a black hole is at its most essential level. A region of space-time where gravity has written a permanent, inescapable sentence. And the story of how that sentence gets written begins with the death of a star. Part 2. The stars that die into darkness. Every star in the universe is engaged in a balancing act that cannot last forever. On one side of that balance is gravity, the relentless inward pull generated by the star's own enormous mass. On the other side is the outward pressure generated by nuclear fusion happening in the star's core. For as long as the fuel holds out, these two forces reach a kind of equilibrium. The star holds its shape. It shines. It burns. The Sun is currently fusing hydrogen into helium at its core at a rate of about 600 million metric tons per second, has been doing this for roughly 6 billion years, and will continue doing it for approximately another 5 billion years before it begins to run out of hydrogen in its core. At that point, the balance shifts. Gravity begins to gain the upper hand. For a star like the Sun, the end comes gently, in cosmic terms. As the hydrogen runs out, the core contracts and heats up, causing the outer layers to expand dramatically. The Sun will swell into a red giant, swelling to perhaps 100 times its current size, likely engulfing Mercury and Venus and possibly Earth. Eventually, the outer layers drift away into space as a glowing cloud of gas called a planetary nebula, leaving behind the dense, cooling core. That core, roughly the mass of the Sun compressed into something about the size of Earth, becomes a white dwarf. The white dwarf then slowly cools over billions of years, fading from a faint ember into an inert lump of cold, dark matter. No black hole. The Sun is not massive enough. But some stars are different. Stars that are born with at least 20 to 25 times the mass of the Sun, and the picture at the end of their lives is completely different. For these stars, the balancing act ends not with a gentle collapse, but with a catastrophic implosion, an event so violent it briefly outshines entire galaxies. To understand why, you need to follow the nuclear fuel chain. A massive star does not simply burn hydrogen. When the hydrogen in the core is exhausted and the core contracts, the temperature rises high enough to begin burning helium, fusing it into carbon and oxygen. When the helium runs out, the carbon begins to burn, producing neon and magnesium. Then neon burns, producing oxygen and magnesium. Then oxygen burns, producing silicon and sulfur. Then silicon burns, producing iron. Iron is where the chain ends. Iron has a nuclear structure that is so stable it cannot release energy through fusion. In fact, fusing iron together absorbs energy rather than releasing it. So when the core of a massive star builds up a ball of iron, roughly the mass of the Sun, no further fusion is possible. The outward pressure supporting the core against gravity drops suddenly and catastrophically to near zero. What happens next takes less than a second. The iron core collapses. In roughly a quarter of a second, a ball of iron, roughly the mass of the Sun and about the size of Earth, is crushed down to an object roughly 10 to 30 kilometers in diameter. The density becomes so extreme that protons and electrons are forced together, combining to form neutrons. The core briefly becomes a neutron star, one of the densest objects in the universe, packing more than a solar mass into a sphere roughly the size of a city. The infalling outer layers of the star hit this suddenly rigid neutron star core like a wall. The impact generates a shock wave that propagates outward through the star at a significant fraction of the speed of light. This shock wave, powered by an enormous burst of neutrinos released from the newly formed neutron star, tears the outer layers of the star apart in a supernova explosion. The explosion is so bright that, at its peak, a single supernova can outshine the entire galaxy of 100 billion stars it belongs to. For a few weeks or months, one dying star burns brighter than 100 billion living ones. Now, here is where the mass of the star becomes decisive. If the iron core that collapses is below roughly 2 to 3 solar masses, the neutron star survives. The neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being compressed into the same quantum state, holds the collapse and gives you a neutron star. That is the end of the story. The neutron star cools, spins, and eventually fades. But if the collapsing core is massive enough, typically estimated at above about 3 solar masses after accounting for mass loss during the explosion, neutron degeneracy pressure is insufficient. No known force in the universe can stop the collapse at this point. The neutron star itself collapses inward, the density increases without limit, and the result is a black hole. Within the black hole, all the mass is compressed into the singularity at its center, a point where our current equations break down completely. The supernova itself is spectacular, a violent detonation that scatters the star's outer layers across light years of space, enriching the surrounding region with carbon, oxygen, nitrogen, iron, gold, and all the other elements forged inside the star over millions of years. But the core, the inmost part of the star, is gone. In its place is darkness, a region of space from which light cannot escape, sitting quietly at the origin point of one of the universe's most violent events. There is a newer and stranger variation on this story that astronomers have now confirmed through observation. Sometimes, a massive enough star does not produce a dramatic supernova at all. Instead, the collapse is total and silent. The core simply implodes, without enough energy being transferred to the outer layers to drive an explosion. The star just vanishes. One moment there is a bright, massive star, and the next there is a black hole and nothing else. No supernova, no glowing nebula, no visible announcement. The star goes dark and does not come back. In 2026, astronomers announced the most detailed set of observations ever assembled of a star, making exactly this transition, a massive dying star in the Andromeda galaxy that skipped the supernova explosion entirely, its core giving way directly under gravity. Rather than exploding outward brilliantly, it simply collapsed. The outer layers were gradually pushed outward by a quiet breath of the dying process. But there was no cosmic fireworks display, just disappearance. Scientists had been watching it for over a decade before it vanished, which is what allowed them to reconstruct what had happened. This silent collapse, where the energy from the implosion is carried away primarily by neutrinos rather than by the kinetic energy of an explosion, has been named complete stellar collapse. It is not rare. It happens. And it is a reminder that the universe does not always announce its most dramatic transitions with fanfare. Sometimes, the most profound changes are the quietest ones. Once a stellar black hole forms, it continues to grow if there is matter nearby to consume. In a binary star system, where 2 stars orbit each other closely, a black hole can siphon gas from its companion star. That gas forms a swirling disk around the black hole, heats to millions of degrees as it spirals inward, and emits powerful X-rays before crossing the event horizon. These X-ray binaries are one of the primary ways astronomers detect stellar black holes. We know of dozens in our galaxy, including the famous Cygnus X1, which was one of the first black hole candidates identified in the 1970s and is now confirmed as a black hole, about 21 times the mass of the Sunday. And then there are the much larger black holes, the ones that are not the final product of a single dying star, but the accumulated mass of millions or billions of stellar masses, or perhaps something built in entirely different ways in the early universe. We will get to those. But first, let us tour the architecture of a black hole itself, because the structure of these objects is extraordinary and full of features that have no analogy in everyday experience. Part 3. The anatomy of a black hole. Imagine descending toward a black hole from a great distance. You cannot see the black hole itself. What you can see from far away is the glowing material that surrounds it. In many black hole systems, there is an accretion disk, a rotating disk of gas and dust and shredded stellar material that has been captured by the black hole's gravity and is spiraling inward. The accretion disk is not the black hole. It is the stuff the black hole is eating, but it is intensely bright, often brighter than entire galaxies, and it is this brilliant ring of light that makes distant black holes visible across billions of light years. As you move closer, the light around you begins to behave strangely. Gravity bends light, and near a black hole, the bending is extreme. Rays of light from the accretion disk behind the black hole are bent around it, producing a ring of light known as the photon ring. Light from the top of the disk bends under the black hole and appears above it. Light from behind appears to wrap around both sides. What you see is not simply the disk as it actually is, but a distorted, lensed version of it, wrapped and bent by the curvature of space-time in ways that make the accretion disk appear to surround the black hole completely, even the parts of the disk that should be behind it. This was confirmed magnificently when the Event Horizon Telescope collaboration released the first images of black holes in 2019 and 2022. The glowing ring surrounding the dark shadow at the center of M87 star, the supermassive black hole in the galaxy Messier 87, and then again around Sagittarius A star at the center of our own Milky Way, is exactly this gravitationally lensed accretion disk light, bent and wrapped around the dark silhouette of the Event Horizon's shadow. Now, as you get closer still, you approach a region called the photon sphere. The photon sphere is located at 1.5 times the Schwarzschild radius, outside the event horizon. It is the orbital radius at which light can travel in a perfect circle around the black hole. A photon aimed precisely at this distance, traveling at exactly the right angle, can theoretically orbit the black hole indefinitely in an unstable circular path. If you were somehow hovering at the photon sphere, you could look ahead and see the back of your own head, because light traveling in a circle would bring your own image around to your eyes. In practice, this circular orbit is unstable. A tiny perturbation pushes the photon either inward, where it falls into the black hole, or outward, where it escapes. But the photon sphere is significant because it is the closest point from which light can still escape the black hole, and it marks the edge of the dark shadow we see in images of black holes. The black circle in those remarkable images from the Event Horizon Telescope is bounded roughly by the photon sphere, which is about 2.5 times larger than the event horizon itself. Below the photon sphere, still outside the event horizon, lies the innermost stable circular orbit, or ISCO. This is the closest point at which matter can orbit the black hole in a stable way without spiraling inward. Inside the ISCO, there are no stable circular orbits. Any infalling material that reaches the ISCO will begin to spiral inward rapidly, crossing the event horizon in a relatively short time. The accretion disk itself extends outward from the ISCO because material closer than this cannot maintain a stable orbit. For rotating black holes, there is another important region called the ergosphere. Rotating black holes are described by a different mathematical solution than non-rotating ones. While the non-rotating Schwarzschild black hole is mathematically simpler, real black holes almost certainly rotate because the stars that form them are rotating and angular momentum is conserved. The rotating black hole solution was found in 1963 by the New Zealand mathematician Roy Kerr and is called the Kerr metric. In a Kerr black hole, the rotation of the black hole drags space-time itself around with it in a phenomenon called frame dragging. Near a rapidly rotating black hole, space-time is literally swept around the equator in the direction of rotation, like water being stirred in a whirlpool. The ergosphere is the region outside the event horizon where this frame dragging is so powerful that nothing can remain stationary, not even light. Any object in the ergosphere must travel in the direction of the black hole's rotation to some extent, no matter what thrust it applies. However, unlike the event horizon, crossing into the ergosphere is not a one-way journey. Objects in the ergosphere can still escape to the outside universe. The ergosphere is not yet the point of no return. The ergosphere has a fascinating theoretical property called the Penrose process, first described by the physicist Roger Penrose in 1969. In principle, an object that enters the ergosphere and splits into two pieces, with one piece falling into the black hole and the other escaping outward, can extract energy from the rotating black hole itself. The escaping piece can leave the ergosphere with more energy than the original object brought in because it has effectively stolen some of the rotational kinetic energy of the black hole. This is not speculation. The physics is solid. In nature, a similar process may operate in the powerful jets of material that blast outward from the poles of some rotating supermassive black holes, extracting energy from the black hole's spin and converting it into some of the most energetic outflows in the universe. Continuing inward, you cross the event horizon. As discussed, from your own perspective, nothing special happens at the event horizon. There is no visible boundary, no sign, no sensation. You cross an invisible geometric threshold in space-time, and from that moment, all paths through space-time lead inward. You cannot stop, you cannot reverse. Every direction in what you experience as space now points toward the singularity. The future, for you, is inward. You have a finite amount of proper time remaining, measured on your own clock, before you reach the center. At the center, according to the mathematics of general relativity, is the singularity. In a non-rotating black hole, the singularity is a single point. In a rotating Kerr black hole, the singularity is a ring, mathematically extended around the equator of the rotation axis. At the singularity, the density becomes infinite, the curvature of space-time becomes infinite, and the equations of general relativity cease to produce meaningful answers. The theory breaks down. This is what physicists mean when they say the singularity is a place where the laws of physics, as we currently understand them, stop working. Most physicists believe the singularity is not a real feature of the universe, but rather a sign that general relativity is incomplete. When quantum mechanics is properly included in the description of space-time at these extreme scales, something very different might be happening at the center of a black hole. Perhaps the density reaches some finite maximum. Perhaps a new geometry emerges. Perhaps, as some speculative theories suggest, the inside of a black hole connects to another region of the universe altogether. We will explore these possibilities later. For now, it is enough to know that the singularity, as general relativity describes it, is where the math stops and the mystery begins. There is one more feature of black hole anatomy worth dwelling on before we move forward, which is the corona. Above and around the accretion disk, closer to the event horizon, many black holes appear to have a region of extremely hot, magnetically dominated plasma called the corona, similar in concept to the sun's corona, but far more extreme. Temperatures in the corona can reach billions of degrees. This corona is responsible for producing the powerful X-ray emission that allows astronomers to detect accreting black holes across vast distances. Exactly how the corona forms, why it has the shape and temperature it does, and how it interacts with the magnetic field threading, the accretion disk, are all areas of active research. The corona can also produce sudden flares, brief, intense bursts of X-ray emission that happen when magnetic field lines snap and reconnect, releasing enormous amounts of energy in a short time. These flares illuminate the accretion disk and allow astronomers to observe the reflection of that illumination, providing a way to measure properties of the black hole, including how fast it is spinning. Put all of this together, and what you have is one of the most architecturally rich objects in the universe. Starting from the outside and working inward. The accretion disk, the jets powered by rotating magnetic fields, the corona, the innermost stable circular orbit, the photon sphere where light orbits, the ergosphere where space-time is dragged by rotation, the event horizon, where the point of no return is crossed, and at the center, the singularity where current physics reaches its limit. Each layer is a different piece of the answer to the question of what a black hole is, and each layer has its own strange physics that took decades of work to even partially understand. Part 4. The family of black holes. Not all black holes are the same. There is a remarkable range of sizes across the black hole population in the universe, and this range is not a smooth continuum. It comes in distinct classes, each with different origins, different environments, and different roles in the cosmic story. The most common type, at least as far as we know, is the stellar black hole. These are the objects we have been discussing so far. They form from the collapse of massive stars, and they typically have masses ranging from about 3 solar masses, roughly the minimum needed to overcome neutron degeneracy pressure, to somewhere around 100 solar masses, depending on the mass of the progenitor star and how much mass was lost during the star's life and in the explosion. Stellar black holes are scattered throughout galaxies, wherever there are or have been populations of massive stars. The Milky Way likely contains somewhere between 100 million and 1 billion stellar mass black holes, the vast majority of them dark and quiescent, not actively accreting, invisible to us. A few dozen have been identified in our galaxy through their X-ray emission or through gravitational wave signals from mergers. Many more have been found in other galaxies using increasingly sensitive instruments. Each detection teaches us something about the formation and growth of these objects, about how massive stars die, and about how black holes interact with their binary companions. The LIGO gravitational wave detectors have alone identified hundreds of black hole mergers since 2015, and the 5th catalog of detections, covering observations from April 2024 to January 2025, contained 161 newly observed events. The pace of discovery has become extraordinary. Then there is the class that sits at the opposite extreme of the size spectrum, supermassive black holes. These are the giants at the centers of galaxies, and their masses are difficult to even put into numbers that feel meaningful. Sagittarius A star, the supermassive black hole at the center of our Milky Way, has a mass of roughly 4 million times that of the Sunday. The black hole at the center of the galaxy, Messier 87, the first black hole ever directly imaged, has a mass of approximately 6.5 billion solar masses. That is not 6.5 billion stars. That is a single object with a mass equal to 6.5 billion suns compressed into a region of space smaller than our solar system. The event horizon of M87 star is so large that if placed at the center of our solar system, it would extend beyond the orbit of Neptune. The event horizon of Sagittarius A star is somewhat more modest, but still enormous by any earthly standard. Its event horizon has an angular size on the sky of about 51.8 microarcseconds, a mind-bendingly small angle that required a telescope effectively the size of the Earth to resolve. That telescope is the Event Horizon Telescope, an array of 8 radio observatories spread across multiple continents, working in coordination to achieve the resolution needed to see the shadow of Sagittarius A star on the sky. The image released in May 2022 showed a bright, slightly uneven ring of light surrounding a dark central region, the shadow cast by the black hole's event horizon. Gas close to the event horizon moves so rapidly, completing a single orbit in as little as 30 minutes, that the ring flickered and changed shape even as the telescopes were observing, making the imaging process enormously more challenging than for the larger and more slowly varying M87 star, where the same orbital period takes about 30 days. The final image of Sagittarius A star was averaged from multiple reconstructed images across different moments in the observation window, capturing the average behavior of the gas over time rather than any single instant. What no one fully understands is how supermassive black holes got so large. The universe is only about 13.8 billion years old. For a black hole to grow from a stellar remnant of a few solar masses to billions of solar masses in that time, it would need to accrete matter and merge with other black holes at an extraordinary rate. Surveys of the early universe using powerful telescopes, including the James Webb Space Telescope, have found supermassive black holes already in place less than 1 billion years after the Big Bang. Billions of solar masses already assembled at a time when the universe was still very young. There is no consensus explanation for how this happened so quickly. Leading theories include the collapse of massive clouds of pristine gas in the early universe, directly into black holes without forming stars first, the rapid growth of stellar black holes in extremely dense early environments, and the possibility that primordial black holes, formed in the first fractions of a second after the Big Bang, seeded the growth of the later supermassive population. Each of these mechanisms is plausible. Each has problems. This remains one of the most active and contested areas of modern astrophysics. Between the stellar black holes and the supermassive ones, there is a conspicuous gap in the observed population called the intermediate mass range, covering roughly 100 to 100,000 solar masses. For years, astronomers could not find them. The gap was puzzling because, if supermassive black holes formed through the gradual accumulation of stellar mass black holes and mergers, there should be a continuous spectrum of masses in between. In recent years, evidence has emerged for intermediate mass black holes in a handful of systems. One candidate, called HLX-1, is estimated to contain about 20,000 solar masses and sits in a region outside the nucleus of a galaxy. Gravitational wave detectors have also found candidates in the intermediate mass range, including some merger products that fall squarely into this gap. The most remarkable finding came in November 2023, when LIGO detected the merger of two black holes with masses of approximately 100 and 140 solar masses, producing a final object roughly 225 times the mass of the Sunday. This event, designated GW231123, holds the record as the most massive binary black hole merger ever detected through gravitational waves, and both progenitor black holes may themselves have been formed through earlier mergers, making this a second or even third-generation black hole. That event is scientifically important because it suggests black holes can grow through hierarchical merging, one merger producing a more massive black hole that then merges again. This chain of mergers could be a pathway toward the intermediate mass range and eventually toward the supermassive range, though the timescales and densities required are significant. Finally, there are primordial black holes, a hypothetical class that, if they exist, would be fundamentally different from all the others, because they would not have formed from collapsing stars. They would have formed in the first fractions of a second after the Big Bang, from regions of the young universe where matter was compressed, especially densely, by the chaotic quantum fluctuations of that earliest moment. If the density in a region exceeded a critical threshold, gravity would have won in a local battle, and a black hole would have formed before any stars existed. The possible masses of primordial black holes span an enormous range, from something as small as the Planck mass, which is fantastically tiny, to many solar masses, depending on when during the early universe they formed. The smaller primordial black holes would have already evaporated through Hawking radiation over the age of the universe. Larger ones might still exist. Primordial black holes are intriguing. As candidates for dark matter, the mysterious, invisible mass that accounts for about 85% of the total matter in the universe. If primordial black holes exist in sufficient numbers and with appropriate masses, they could account for some or all of the dark matter without requiring any new fundamental particles. Observations have constrained but not ruled out this possibility for certain mass ranges. The search continues. Each class of black holes is a different chapter in the story of how the universe organizes gravity and matter across cosmic time. Together they form a family whose diversity reflects the diversity of the processes that create and grow them, from the violent deaths of individual stars to the titanic mergers of entire galactic nuclei across billions of years. Part 5. What happens when you fall in? Let us walk through something slowly and carefully. The experience of falling into a black hole. Not the violent, dramatic version you might imagine, but the real physics of it, which is simultaneously stranger, more nuanced, and more genuinely haunting than any science fiction version. Begin from a great distance. You are in a spacecraft, and you are approaching a stellar mass black hole, something with perhaps 10 times the mass of the Sunday. From far away, the black hole's gravity is not dramatically different from that of any other object of the same mass. If the Sun were replaced by a black hole of exactly the same mass, Earth's orbit would not change at all. Black holes do not suck. They do not reach out and grab things beyond their normal gravitational range. Their gravity obeys the same inverse square law as everything else. The dramatic effects only become apparent when you get very close. As you fall inward and the black hole grows larger in your instruments, you will notice your instruments detecting X-ray radiation from the accretion disk if the black hole is actively accreting. You will see the visual distortion of background stars growing as gravitational lensing bends the paths of light. Stars that should be behind the black hole appear to shift around its edges, their images stretched and duplicated by the extreme curvature of space-time. Closer now, and here is where the physics becomes genuinely remarkable. The gravitational field you are falling into is not uniform. The side of your body, or your spacecraft, that is closer to the black hole is being pulled harder than the side farther away. This difference in gravitational pull across the extent of your body is called a tidal force, and it stretches you radially toward the center while compressing you from the sides. Think of what the moon does to the oceans. The side of Earth facing the moon is pulled harder than the far side, creating a bulge of water on both the near side and the far side. That is a tidal effect from the moon's gravity. Near a black hole, these tidal forces become extraordinary. For a stellar mass black hole with a mass of around 10 solar masses, the tidal forces at the event horizon are so extreme that they would shred a human body into a thin strand before ever reaching the horizon. You would be pulled apart lengthwise and compressed from the sides, the process that astronomers call spaghettification, because the result is not entirely unlike what happens to spaghetti dough being stretched. For supermassive black holes, the situation is surprisingly different. The event horizon of a supermassive black hole is so large that the tidal forces at the horizon itself are actually relatively mild. You might cross the event horizon of a billion solar mass black hole without feeling anything particularly dramatic. The tidal gradient is proportional to the inverse cube of the distance from the center, and for a sufficiently large black hole, the event horizon is so far from the center that the gradient across a human-sized object is gentle. You cross the point of no return, without ceremony, without pain, without physical drama. You are simply inside, and there is no way out. The recognition of this depends entirely on the scale of the black hole you are dealing with. For stellar mass black holes, you are destroyed, far outside the horizon. For the largest supermassive black holes, you might pass through without immediate discomfort, traveling perhaps thousands of kilometers past the event horizon, before tidal forces eventually become enough to destroy you as you fall toward the singularity. Now, from the perspective of a distant observer watching you fall toward the black hole, something else entirely is happening. As you approach the event horizon, your clock appears to run more and more slowly compared to their clock. This is gravitational time dilation, a real and measurable effect of general relativity. Gravity slows time. The stronger the gravitational field, the slower time passes relative to a region of weaker gravity. Clocks run slightly slower at sea level than on mountaintops, and this is not a negligible effect. The GPS satellites orbiting Earth need to account for gravitational time dilation to maintain their accuracy. Without the correction, GPS errors would accumulate at a rate of about 45 microseconds per day, eventually making the system useless. Near a black hole, this effect is not a subtle correction, but the dominant reality. As you approach the event horizon, the distant observer sees your clock slow more and more dramatically. The light you emit is redshifted to longer and longer wavelengths, shifting from visible light to infrared to radio waves. You become dimmer and dimmer. Your image freezes asymptotically close to the horizon, never quite reaching it from the observer's perspective, because the light from your final moments is infinitely redshifted and takes an infinitely long time to climb out of the gravity well. You are effectively frozen in time at the horizon, a fading, reddening image, preserved for the distant observer at the threshold you will never appear to cross. But you crossed it. From your own reference frame, your clock kept ticking normally. Time did not slow down for you. You felt the falling. You had experiences. You continued moving inward. The two perspectives are not in contradiction. They are simply descriptions of the same events from two different reference frames in curved space-time, and both descriptions are correct within their own frame. This is one of the most conceptually challenging things about black hole physics. The intuition that there must be a single, agreed-upon sequence of events that every observer can agree on is simply wrong when space-time is curved this severely. What is simultaneous to one observer is not simultaneous to another. What appears to be a moment frozen for the outside observer is an ongoing experience for the infalling observer. Reality near a black hole has a kind of radical perspectivism built into it at a fundamental level. Once inside the event horizon, the future changes its meaning. Outside the horizon, you can choose to move in many directions through space while time advances unavoidably forward. Inside the horizon, the radial direction toward the singularity becomes time-like. What this means, in a deeply strange way, is that you cannot avoid the singularity any more than you can avoid tomorrow. The singularity is in your future, inside the event horizon, the way that tomorrow's date is in your future outside it. No amount of thrust, no engine, no energy source can reverse that direction. You have not just crossed a spatial boundary. You have entered a region where the geometry of space-time itself points inward. The time remaining between crossing the event horizon and reaching the singularity depends on the mass of the black hole. For a stellar mass black hole of 10 solar masses, that time is roughly a tenth of a millisecond. For the supermassive black hole at the center of M87, the time from horizon crossing to singularity would be measured in hours. And for a large primordial black hole, or especially massive remnant, perhaps longer still, in each case, the journey ends at the singularity. What happens there, what the singularity actually is at a physical level rather than a mathematical one, remains unknown. We will return to that question. There is one more element of the infalling experience worth dwelling on. As you fall inward and the universe outside the event horizon becomes more and more distant, the light from the outside universe is blue-shifted. The photons from the universe outside are falling inward along with you, but they are concentrated into a smaller and smaller solid angle as you fall, making the sky outside appear compressed into a smaller and smaller bright patch ahead of you. The rest of the sky is black. The universe shrinks into a bright circle ahead of you as you fall towards something whose nature physics cannot yet fully describe. Part 6. The monster at the center of the Milky Way. For most of human history, the center of our galaxy was invisible to us. Not because no one was looking, but because the galactic center is separated from Earth by thousands of light years of gas and dust, so thick that visible light cannot penetrate it. You cannot see the center of the Milky Way with your eyes, even on the clearest night. The dust absorbs and scatters visible wavelengths completely. What astronomers found when they began working in radio wavelengths and later infrared wavelengths that can pass through the dust was a dense, chaotic region packed with billions of stars, vast clouds of molecular gas, strong magnetic fields, and at its very heart, a compact radio source. This source, discovered in 1974, was given the designation CGR-A for Sagittarius A because it lies in the direction of the constellation Sagittarius. A brighter, more compact component at the center of the larger source was later identified and designated Sagittarius A star, written as SCRA-A. For years, the nature of SCRA star was debated. It was clearly compact. It emitted radio waves and X-rays. It was clearly massive, based on the speed of the gas clouds surrounding it. But was it a black hole, or something else? Some astronomers proposed that it could be a compact cluster of stars, or a dense agglomeration of dark matter, or some other exotic configuration that might mimic certain properties of a black hole without actually being one. The question was resolved gradually and definitively by one of the most patient and exacting observational campaigns in the history of astronomy. Beginning in the early 1990s and continuing for decades, two independent teams of astronomers, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, and the other led by Andrea Ghez at UCLA, measured the orbits of individual stars near the galactic center with increasing precision. These stars, called the stars, were visible in the infrared through the galactic dust, and their orbits were extraordinary. S2, one of the most closely watched, completes an orbit around the galactic center in approximately 16 years, with a closest approach, called the pericenter passage, of only about 120 astronomical units from SCRA-A star. 120 astronomical units is just over 3 times the distance from the Sun to Neptune. A star passing within that distance of an object whose mass is 4 million times that of the Sun is moving fast. During its closest approach in 2018, S2 was clocked at about 7,600 kilometers per second, roughly 2.5% of the speed of light. The orbital data were conclusive. No cluster of stars, no dark matter concentration, no other known physical arrangement could explain the observed orbits. The mass, 4 million solar masses, was contained within a region smaller than the orbit of S2. The only physical object that could be that massive and that compact was a black hole. In 2020, the Nobel Prize in Physics was awarded to Penrose for his theoretical work on black holes, and to Ghez and Genzel jointly for their discovery of a supermassive compact object at the galactic center. It was official recognition that Sagittarius A star is a black hole. But having conclusive indirect evidence through stellar orbits is different from actually seeing the object directly. For that, a completely different kind of telescope was needed. Not an optical telescope, which cannot penetrate the galactic dust. Not a single radio dish, which lacks the resolution to see something so small. What was needed was a telescope the size of the Earth. The Event Horizon Telescope achieves this extraordinary effective size through a technique called very long baseline interferometry. Multiple radio telescopes spread across the globe observe the same target simultaneously, recording the radio waves arriving at each site. The recordings are then combined computationally, using the known positions and timing of the different telescope sites to reconstruct the signal as it would have been recorded by a single telescope with a diameter equal to the maximum separation between the real telescopes. The maximum separation of EHT sites is roughly the diameter of the Earth, about 12,742 kilometers, giving the array an angular resolution fine enough to see an orange sitting on the surface of the Moon from Earth. The first EHT observations targeted CGR A star were made in April 2017, using data from 8 radio observatories, including the South Pole Telescope in Antarctica, the Atacama Large Millimeter Array in Chile, the IRAM telescope in Spain, the Submillimeter Array in Hawaii, and others. The data were then shipped on hard drives to processing centers in the United States and Europe because the data rates were too high for any available internet connection to transmit them. Petabytes of data, flown on planes from telescopes on multiple continents, assembled and processed over years. The result was unveiled on the 12th of May, 2022, the first direct image of SCRA A star. A glowing ring of light, slightly uneven and lumpy, surrounding a dark central region. The ring is formed by light from the accretion disk, bent and wrapped around the black hole by its gravity. The dark region is the shadow cast by the event horizon. It is not the black hole itself that is dark, it is that the black hole captures light from behind it, creating a dark region silhouetted against the bright glowing ring. The image confirmed what stellar orbits had long suggested. The angular size of the shadow matched predictions based on the known mass and distance of Screen A star to remarkable precision. The image was described by Fariel Ozel, a member of the EHT scientific team, as the biggest test of Einstein's theory of general relativity ever made. The theory passed. What makes SCRA A star particularly interesting compared to the earlier image of M87? Star is the speed at which gas moves around it. M87. Star is about 6.5 billion solar masses and sits about 55 million light-years away. Because it is so much more massive, the innermost orbit around M87 star takes about 30 days. Gas completes one orbit in roughly a month, which means the structure of the accretion disk changes slowly enough that the EHT could observe it for weeks and produce a relatively stable averaged image. SCRA A star, smaller and closer, has an innermost stable orbit of only about 30 minutes. The gas whips around in the time it takes to watch a short film. The structure of the disk changes dramatically during a single observing session. Making a clean image required averaging over many different configurations of gas, which is why the final image has a slightly blurred, averaged quality rather than the crisp, fine detail you might expect. The underlying physics is not less interesting for the blurring. It is in some ways more interesting because it means SCRA star is a highly dynamic, rapidly varying system, one that flares and brightens and changes structure on timescales of minutes. Why does SCRA star have an accretion disk at all, given that it is relatively quiescent by the standards of supermassive black holes? The answer is that there are stars and gas clouds relatively close to the galactic center, and their stellar winds and occasional close passages feed a trickle of matter toward the black hole. SCRA A star is not a particularly hungry black hole at the moment. Compared to the blazing quasars powered by supermassive black holes consuming enormous quantities of matter in the early universe, SCRA A star is barely nibbling, but it flares. In X-rays, flares from Skrar A star are observed regularly, sometimes several per day. These flares are brief, energetic events, likely caused by magnetic reconnection or the disruption of infalling gas clumps close to the event horizon. Evidence published in 2026 suggested that wind is blowing outward from Skrar star, the result of gas being heated by the black hole's activity to the point where it escapes rather than falling in. This outflow, detected after a search that had been ongoing for half a century, affects the galactic environment around the center of the Milky Way in ways that are still being studied. There is a quality to the idea of Sagittarius A star that I want to linger on for a moment, because it reframes the entire Milky Way in a way that does not always get sufficient attention. Every star you can see in the night sky, every star in the Milky Way, is orbiting the galactic center. And at that center, quietly, without visible fanfare, sits a black hole 4 million times the mass of our Sunday. It has been there for billions of years. Every orbit our sun has made around the galactic center, all 20 of them over the 4.6 billion year history of the solar system, has been an orbit around this invisible object. The spiral arms of the galaxy, the disk, the stellar populations, they are all, in a sense, arranged around this singularity at the heart of it all. Skrar A star is not just a curiosity at the edge of our understanding. It is the gravitational anchor of our home. Part 7. Hawking Radiation and the Slow Evaporation. In 1974, Stephen Hawking announced a result that shocked the physics community. Black holes, he said, are not perfectly black. They radiate, they lose mass, and given enough time, they evaporate completely. This was not what anyone expected. The whole concept of a black hole, the fundamental defining property, is that nothing escapes. Light does not escape. Matter does not escape. How could radiation escape? The answer lies not in general relativity, but in quantum mechanics. And the interaction between the two produces one of the most profound and counterintuitive results in all of theoretical physics. To understand Hawking radiation, you need to understand something about quantum mechanics and the vacuum of space. Classical physics describes empty space as simply that, empty, no particles, no energy, nothing. But quantum mechanics tells a different story. In quantum field theory, the vacuum is not empty at all. It is a seething, fluctuating sea of virtual particle-antiparticle pairs that spontaneously pop into existence and annihilate each other so quickly that they cannot be directly detected. These virtual particles are a consequence of the Heisenberg uncertainty principle, which permits temporary violations of energy conservation as long as they are resolved quickly enough. Now, bring a black hole into the picture. At the event horizon, this pair creation process has a remarkable consequence. When a virtual particle-antiparticle pair appears near the event horizon, one particle might fall inward across the horizon, while the other escapes outward. Normally, the pair would annihilate almost immediately. But if one member crosses the horizon before they can recombine, the pair is separated. The outgoing particle, now real rather than virtual, escapes into space. From the perspective of an observer far from the black hole, a real particle has been emitted. The black hole appears to be radiating. Where does the energy for this radiation come from? The black hole itself. The particle that falls inward effectively has negative energy in the black hole's reference frame, reducing the black hole's total mass energy by a tiny amount. Over time, this loss of mass accumulates. The black hole very slowly loses mass to Hawking radiation. Hawking's calculation showed that the radiation from a black hole is precisely thermal, meaning it has the same statistical distribution as radiation from an object glowing because of its temperature. The temperature of a black hole's Hawking radiation is inversely proportional to its mass. A stellar mass black hole, 10 times the mass of the Sun, has a Hawking temperature of about 6 billionths of a Kelvin. Colder than the coldest thing in the universe, far colder than the cosmic microwave background radiation, which bathes the universe at about 2.7 Kelvin. This means a stellar mass black hole actually absorbs more energy from the cosmic microwave background than it radiates in Hawking radiation. It grows rather than shrinks. For a stellar mass black hole to begin net evaporation through Hawking radiation, the universe would need to cool below the black hole's Hawking temperature, which won't happen for an unimaginably long time. The Hawking evaporation time of a stellar mass black hole is roughly 10 to the power of 67 years. The current age of the universe is about 13.8 billion years, which is approximately 10 to the power of 10 years. The evaporation time is longer than the current age of the universe by a factor of 10 to the 57. It is not going to happen on any timescale we have a word for. For a supermassive black hole of 5 billion solar masses, like M87, star, the Hawking evaporation time extends to roughly 10 to the power of 100 years, a number that makes the stellar mass evaporation time look brief. Long after the last star in the universe has died, long after the cosmic microwave background has cooled to nothing, long after protons have potentially decayed, these supermassive black holes will still be sitting there, radiating their barely perceptible warmth into the ultimate cold of a universe that has run out of everything else. But at the other end of the mass scale, things are very different. A sufficiently small black hole radiates much more intensely. The temperature scales inversely with mass, so a black hole with the mass of a mountain, compressed into the size of an atomic nucleus, would have a Hawking temperature of billions of Kelvin and would be blazing with gamma radiation. Such a black hole would evaporate in a fraction of a second. The final stages of black hole evaporation are thought to be explosive, a burst of high-energy radiation as the last of the mass disappears. Primordial black holes with very small masses, those that formed in the early universe with less than about 10 to the 12 kilograms of mass, or roughly the mass of a large asteroid, would have completely evaporated by now through Hawking radiation. Primordial black holes that formed with more mass than this threshold would still exist. The search for the distinctive gamma-ray signature of small, evaporating primordial black holes is an ongoing area of observational research. Hawking radiation, beyond its implications for the eventual fate of black holes, also opened one of the deepest problems in theoretical physics, a problem that has occupied the best minds in physics for half a century and remains, as of today, genuinely unresolved. It is called the black hole information paradox, and it deserves its own section. Part 8. The information paradox. At the heart of quantum mechanics is a principle called unitarity. It says, in essence, that information is never truly lost. If you know the complete quantum state of a physical system at one moment, the laws of quantum mechanics allow you to evolve that state forward in time or backward in time and recover the complete state at any other moment. The physics is reversible. Information is conserved. This is not just a convenience of quantum mechanics. It is a foundational requirement. If unitarity were violated, quantum mechanics itself would collapse into inconsistency. Probabilities would not add up to 1. The theory would fail. Now consider what happens when matter falls into a black hole. Information about the infalling matter is carried inside the event horizon. The composition of the infalling material, the quantum states of every particle, the information encoded in every degree of freedom, all of it crosses inward. From outside the black hole, none of this information is accessible. The black hole is characterized, according to the no-hair theorem of general relativity, by only 3 properties: its mass, its angular momentum, and its electric charge. 2 black holes with identical mass, spin, and charge are physically identical from the outside, regardless of whether one formed from the collapse of iron and nickel and the other from a ball of cotton candy. The details of what went in are lost from the exterior description. Then Hawking radiation carries mass away from the black hole. The radiation is thermal, perfectly featureless, carrying no information about what fell in beyond the basic mass energy. As the black hole radiates away all its mass, the information about everything that ever fell into it has to go somewhere. But thermal radiation does not carry that information. And when the black hole is gone, completely evaporated, where is the information? This is the information paradox. Either the information is destroyed, which violates unitarity and undermines quantum mechanics, or the information is somehow encoded in the Hawking radiation in a subtle, non-obvious way. Or the information remains in some form after the black hole evaporates, perhaps in a remnant object at the Planck scale. Or the question itself rests on incorrect assumptions about how Hawking radiation actually works. Each resolution has serious problems. Destroying information means abandoning a cornerstone of quantum mechanics. Encoding information in Hawking radiation requires quantum correlations between early and late radiation that seem to violate the smooth geometry of the horizon assumed in Hawking's original calculation. Remnants create other problems, and modifying the assumptions about Hawking radiation brings you into contact with the firewall paradox, proposed in 2012 by physicists Almheri, Marolf, Polchinski, and Sully, which suggested that if information is preserved in Hawking radiation, the event horizon must be replaced by a wall of high-energy radiation, a firewall, that would destroy any infalling observer, rather than allowing them to cross the horizon smoothly. This seems to violate the equivalence principle, a pillar of general relativity. The information paradox is not a peripheral technical puzzle. It sits at the intersection of the two greatest theories in physics, general relativity and quantum mechanics, and it reveals that these theories are mutually incompatible in an important way. They cannot both be right as they currently stand. Something has to give. Progress has been made. In 2019, a group of researchers, including Netta Engelhardt at MIT, published a calculation using tools from string theory and the holographic principle, suggesting that the entropy of Hawking radiation follows a curve called the Page curve, rising and then falling as the black hole evaporates. This Page curve behavior is what you would expect if information is preserved in the radiation, because the entropy of a subsystem of a larger system should eventually decrease as the subsystem encodes the correlations of everything else. The calculation suggested that information is not lost, at least not in the way Hawking's original calculation implied, but the precise mechanism by which information gets encoded in the outgoing radiation remains unclear. The holographic principle, which grows out of the study of quantum gravity and string theory, proposes that all the information about a volume of space is encoded on the boundary of that volume, like a hologram, where a three-dimensional image is encoded in a two-dimensional surface. For a black hole, this would mean that everything falling in is somehow encoded on the event horizon surface, and the Hawking radiation carries that information back out as the horizon area decreases. This is a compelling conceptual picture, but translating it into a precise, calculable mechanism that resolves all the paradoxes remains an open problem. What is certain is this: the information paradox has driven some of the deepest theoretical advances in physics over the past several decades. Ideas like string theory, holography, the ADS, CFT correspondence, quantum error correction, and the island formula in quantum gravity have all emerged partly from the effort to understand what black holes do to information. The black hole is not just an astrophysical curiosity. It is a theoretical laboratory where our deepest ideas about physics are being tested and sometimes broken. The paradox may not be resolved in our lifetimes, or it may be resolved in the next decade with a breakthrough that seems obvious in retrospect. That is the nature of genuinely hard problems in physics. Part 9. Black Holes and the Fabric of Space-Time. One of the most extraordinary scientific achievements of the past century happened on the 14th of September, 2015, at 5:51 in the morning Eastern Time. Two detectors separated by about 3,000 kilometers, one in Livingston, Louisiana, and one in Hanford, Washington, simultaneously registered a tiny but unmistakable stretching and squeezing of space-time itself. The signal lasted about 0.2 seconds. It was later analyzed and identified as the signature of two black holes, one weighing about 29 solar masses and one weighing about 36 solar masses, spiraling together and merging into a single black hole of about 62 solar masses, approximately 1.3 billion light-years away. The missing 3 solar masses worth of energy had been radiated away as gravitational waves. This was the first direct detection of gravitational waves. It was also the first direct observation of a binary black hole system and the first detection of black holes in the mass range of 29 and 36 solar masses. The discovery was made by the LIGO detectors, the Laser Interferometer Gravitational Wave Observatory, and in 2017, the physicists who founded and developed LIGO, Rainer Weiss, Barry Barish, and Kip Thorne, were awarded the Nobel Prize in Physics. Gravitational waves are ripples in space-time itself, predicted by Einstein in 1916 as a consequence of his general theory of relativity. Just as moving charges produce electromagnetic waves, moving masses produce gravitational waves. A single mass moving uniformly does not produce gravitational waves, because its gravitational field simply moves with it. But a mass that accelerates, or more precisely, a system with a changing quadrupole moment of its mass distribution, radiates gravitational waves. Two massive objects orbiting each other in a binary system are exactly such a system. As the two black holes in a binary system orbit each other, they radiate gravitational waves. This radiation carries energy away from the system. As the system loses energy, the two black holes spiral closer together. The orbital period decreases. The gravitational wave frequency increases. The amplitude of the waves grows. The two black holes accelerate toward merger. In the final fractions of a second before merger, the gravitational wave frequency reaches its peak, a characteristic rising chirp called the in-spiral, followed by the merger itself, and then a ring-down as the newly formed merged black hole settles into a stable, rotating configuration, emitting a brief, decaying burst of gravitational waves. The LIGO detectors measure this signal as an incredibly tiny displacement. The arms of each LIGO detector are 4 kilometers long, and the detectors can measure changes in the relative length of the arms at the level of 1,000th the diameter of a proton. This is not a metaphor. The gravitational wave signal from that first detection, arriving from 1.3 billion light-years away, stretched and compressed the 4-kilometer arms of LIGO by about 4 times 10 to the negative 18 meters, a distance 1,000 times smaller than the diameter of a proton, 300 million times smaller than a hydrogen atom. The detection of gravitational waves opened an entirely new way of observing the universe. Before LIGO, all astronomy was based on electromagnetic radiation of various wavelengths: visible light, radio waves, X-rays, infrared, ultraviolet, gamma rays. Gravitational waves are something fundamentally different. They are not electromagnetic. They travel at the speed of light, but they interact so weakly with matter that they pass through everything without being absorbed or scattered. A gravitational wave from a black hole merger 1.3 billion light-years away passes through you, through Earth, through the Sun, through the Milky Way, without any significant attenuation. This is what makes detecting them so difficult, and why it took decades to build detectors sensitive enough to register them. It is also what makes them uniquely valuable. They carry information from some of the most extreme environments in the universe, environments that produce no electromagnetic radiation, and they deliver that information uncorrupted across billions of light-years. Since the first detection in 2015, the catalog of gravitational wave events has grown dramatically. By the time the 5th gravitational wave catalog was released, covering observations from April 2024 through January 2025, 161 new events had been added from that period alone. The LIGO detectors, upgraded between observing runs, along with the Virgo detector in Italy and the Kagra detector in Japan, are now detecting gravitational wave events at a rate of 3 to 4 per week during active observing periods. Among these hundreds of detections, some stand out for what they reveal. The event designated GW231123, detected on the 23rd of November, 2023, resulted in the most massive binary black hole merger yet observed. The two merging black holes had masses of approximately 137 and 100 solar masses, producing a final object of roughly 225 solar masses. Both progenitor black holes were in or above a mass range called the pair instability gap, a range of masses between roughly 50 and 130 solar masses, where the physics of stellar evolution suggests stellar black holes should not form through standard collapse. The existence of black holes in this mass range implies they formed through earlier mergers, making GW231123 potentially a third-generation black hole, the product of multiple prior merger events in a dense stellar environment like a globular cluster. Each gravitational wave detection is simultaneously an astrophysical discovery and a test of general relativity. The observed waveforms can be compared in extraordinary detail to predictions from numerical solutions of Einstein's equations. Every detection so far has matched the predictions of general relativity to the precision of the measurement. The ring-down phase, in which the newly formed black hole settles into a stable state, is particularly sensitive to the details of the black hole geometry. Analysis of ring-down signals from multiple mergers has confirmed that the merging objects are consistent with black holes, as described by general relativity, with no indication of any additional structure or deviation from the Kerr metric. Two particularly unusual events detected in October and November 2024, designated GUD 241011 and GU 241110, involved black holes with spins that were misaligned from their orbital motion in ways that indicated these systems had complex formation histories. GW 241110 was especially remarkable because the primary black hole was spinning in a direction opposite to its orbital motion, the first time this retrograde spin had been clearly observed. Systems with this kind of misaligned spin are predicted to form when black holes pair up dynamically in dense stellar environments, rather than forming together from a binary star system. These two events were described by astronomers as providing the first direct evidence for this class of dynamically assembled binaries. There is something almost meditative about gravitational wave astronomy. Somewhere in the universe, two black holes spiral together over millions of years. In the last few fractions of a second, they release more energy in gravitational waves than all the stars in the observable universe emit in electromagnetic radiation during that time. That pulse of space-time curvature ripples outward at the speed of light. A billion years later, it reaches Earth and nudges the mirrors of a detector by a distance smaller than an atom. And we know it happened. We know the masses, the spins, the distance, the merger dynamics. We know it from a tremor in space-time that passed through every atom on Earth and registered in mirrors cooled close to absolute zero. That is one of the most remarkable things human civilization has ever done. Part 10. The deepest mysteries still unsolved. We have now traversed a great deal of what physics understands about black holes. But understanding is always an island in a sea of mystery, and for black holes, the surrounding waters are particularly deep and particularly dark. Let us spend this final section sitting with the things we genuinely do not know. The questions that the best physicists in the world are working on right now, questions that may not be answered for decades or may require a conceptual revolution we cannot yet see coming. The first, and perhaps most fundamental, is the singularity problem. At the center of every black hole, according to general relativity, is a singularity, a point or ring where density becomes infinite, where curvature becomes infinite, and where the equations of the theory produce meaningless results. Physicists universally believe that singularities are not real features of the universe. They are signs that the theory has been pushed beyond its domain of validity. The same way that Newtonian gravity breaks down when objects approach the speed of light, general relativity breaks down at the Planck scale, where the energy densities and curvatures are so extreme that quantum effects on space-time geometry cannot be ignored. What actually happens at the center of a black hole, when the correct quantum theory of gravity is applied, is unknown. The leading candidate theories, loop quantum gravity and string theory, make different predictions, and neither has been tested at these extreme scales. Loop quantum gravity suggests that space-time is discrete at the Planck scale, a network of quantum spin states rather than a smooth continuum, and that this discreteness prevents singularities from forming. Instead of a singularity, there might be a region of extremely high but finite density, where the quantum nature of space-time becomes dominant. String theory suggests its own resolution, involving extended objects and higher dimensions. In early 2025, a research team published a paper in Physics Letters B, demonstrating mathematically that an infinite series of higher-order gravitational corrections, the kind of corrections that quantum gravity is expected to produce, can eliminate singularities and result in what are called regular black holes with no singular center. If this mathematical result corresponds to the actual physical situation in the universe, then the center of every black hole is not a point of infinite density, but a region of extraordinary but finite curvature, where quantum gravity effects become dominant and the current description of space-time fails to apply. What exactly occupies that region, what the physics of that extreme interior looks like, is genuinely open. There is a related and speculative question about what might be on the other side. In some theoretical frameworks, the Einstein field equations permit solutions called Einstein-Rosen bridges, more commonly known as wormholes. A wormhole is a hypothetical tunnel through space-time connecting two separate regions, which might be far apart in ordinary space or even belong to different universes entirely. Some theorists have proposed that the singularity at the center of a black hole connects to a corresponding singularity in a white hole, a hypothetical time-reversed black hole that expels rather than absorbs matter. A white hole would be the time reverse of a black hole. Where a black hole is a region of space-time that can never be exited, a white hole is a region that can never be entered, but from which matter and energy continuously emerge. Nothing can fall into a white hole. Everything pops out of it. Mathematically, white holes are valid solutions to Einstein's equations. Physically, there is no known mechanism to produce them, and no observational evidence for their existence. But they are not ruled out, and some theories of quantum gravity suggest that as a black hole evaporates through Hawking radiation, what begins as a black hole eventually transitions into a white hole as the information it contains is expelled. This would be a striking resolution to the information paradox, but whether it corresponds to physical reality is unknown. The question of dark matter connects to black holes in a way that is still being actively explored. Primordial black holes, as discussed earlier, might constitute some or all of the dark matter. Detailed observations of gravitational microlensing, where a massive object passes in front of a background star and briefly brightens it through gravitational lensing, have constrained the contribution of primordial black holes to dark matter for several mass ranges. But windows remain open, and the detection of gravitational waves from black hole mergers is now also being used to constrain the primordial black hole population in new ways. There is the question of how supermassive black holes grew so large so quickly in the early universe. The James Webb Space Telescope has continued finding supermassive black holes at high redshifts in the first billion years of cosmic history that are already hundreds of millions or billions of solar masses. Getting a black hole to that mass that quickly requires either extreme accretion rates or seeding from unusually massive initial objects, or perhaps a mechanism we have not identified. This is one of the most active and contested areas in observational and theoretical astrophysics. There is the question of what happens at the endpoints of black hole evaporation. As a black hole evaporates through Hawking radiation and approaches the Planck mass, roughly 22 micrograms, the quantum gravity effects become completely dominant. The evaporation rate diverges. The temperature diverges. What happens in the final moments of black hole evaporation is unknown. Does the black hole disappear entirely in a final explosive burst? Does it leave behind a stable Planck mass remnant? Does it somehow convert into a white hole? The answer to this question is likely connected to the resolution of the information paradox and to a deeper understanding of quantum gravity. Then there is the question of whether black holes might connect different regions of the universe in ways we have not anticipated. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, suggests a deep connection between wormholes in general relativity and quantum entanglement in quantum mechanics. The name comes from the abbreviations of the two concepts, the Einstein-Rosen bridge for wormholes and the Einstein-Podolsky-Rosen paper on quantum entanglement. The conjecture proposes that two entangled particles are connected by a microscopic wormhole, that entanglement and geometry are different descriptions of the same underlying physical connection. If correct, this would represent a profound unification of quantum mechanics and gravity, but it remains speculative and mathematically incomplete. And perhaps the deepest question of all, what is the correct theory of quantum gravity? General relativity works beautifully at the scales of planets, stars, and galaxies. Quantum mechanics works beautifully at the scales of atoms and subatomic particles. But these two theories are incompatible in their mathematical foundations. At the extreme densities of black hole singularities, or at the conditions of the very early universe, both theories must be relevant, and they cannot both be right as currently formulated. Finding the theory that supersedes both, that reduces to general relativity in the appropriate limit and to quantum mechanics in the appropriate limit, while giving a correct description of the extreme regime where both fail, is the central challenge of theoretical physics. String theory, loop quantum gravity, causal dynamical triangulation, causal set theory, asymptotic safety, and several other frameworks are being actively explored as candidates. None has yet made a clear, experimentally confirmed prediction that distinguishes it from the others and from existing theories. The problem is that the scales where quantum gravity effects would be most dramatic, Planck scale physics, are approximately 16 orders of magnitude smaller than what any current or foreseeable particle accelerator can probe. Discovering quantum gravity effects may require astronomical observations rather than laboratory experiments, making black holes, neutron stars, gravitational waves, and the cosmic microwave background our primary laboratories. Black holes sit at the intersection of all of this. They are the places in the observable universe where gravity is most extreme, where space-time curvature is greatest, where quantum gravity effects, though still far smaller than what any instrument can currently resolve, are most relevant. Understanding black holes fully means understanding gravity, fully means understanding quantum mechanics, fully means finding the unified theory that resolves the deepest incompatibilities in our description of nature. That is the real reason physicists are so fascinated by black holes. Not just because they are dark and dramatic and death-dealing in every science fiction story ever written about them, but because they are the universe's way of asking physics its hardest questions. They are natural experiments that probe the deepest structure of space, time, matter, and information, at scales and energies we cannot recreate in any laboratory. Every observation of a black hole, every gravitational wave detection, every image from the Event Horizon Telescope, every measurement of stellar orbits around Sagittarius A star is a piece of data in an experiment that has been running for billions of years in some corner of the universe, waiting for creatures clever enough to learn how to read it. We are just beginning to learn. The observations over the past decade, from the first gravitational wave detection in 2015 to the images of Sagittarius A star in 2022, to the extraordinary catalog of mergers compiled through 2025, represent a transformation in our ability to study these objects. We have gone from theorizing about black holes to imaging them, to detecting the ripples they send through space-time itself, to cataloging hundreds of mergers and using them to test general relativity with unprecedented precision. And yet, the center of the black hole remains inaccessible. The information paradox remains unsolved. The origin of supermassive black holes remains unclear. The endpoint of Hawking evaporation remains unknown. The singularity remains a place where our best theory raises its hands and admits it cannot proceed. The correct quantum theory of gravity remains undiscovered. These are not failures. They are the shape of genuine frontier science. The map of knowledge always has edges, and the edges of our knowledge about black holes are some of the most interesting and productive edges in all of physics. Every question that cannot yet be answered is an invitation to the next generation of physicists, astronomers, mathematicians, and theorists. Somewhere in the universe right now, two black holes are spiraling toward each other, their orbit tightening over millions of years. When they finally merge, in some future moment, the gravitational waves from their collision will spread outward through space-time at the speed of light. Billions of years from now, those waves might pass through what will then exist at the coordinates where Earth is or was. Whether anyone will be there to detect them, whether the instruments they would need to register that signal will have been built, whether the civilization that would interpret the data will have learned enough to understand what those waves are saying is unknowable. But the wave will be real. The space-time ripple from the merging of two darkness-wrapped masses, two singularities, wrapped in event horizons, will be as real as anything in the universe, passing through everything, disturbing nothing we could easily notice. A message from the universe's most extreme environments, traveling at the speed of light, waiting for eyes clever enough to read it. That is what a black hole is. Not just a darkness in space, not just a drain, not just a region of no return. It is a place where the universe is asking its deepest questions about itself. A place where matter has gone to its extreme. A place where our physics meets its limits and invites us to go beyond them. And in the quiet of this moment, sitting with all of that, the darkness is not empty. It is full of things we are still learning to see. If you have made it this far, Thank you. That means a lot. There is something genuinely wonderful about spending hours together in the depths of one of the universe's most captivating mysteries, and I hope it brought you some peace and some wonder in equal measure. Drop a comment if you enjoyed this. Tell me which part surprised you most, or which question about black holes you find yourself unable to stop thinking about. Comments like that keep this channel alive and remind me why I make these videos in the first place. If you are new here and you like the pace and the depth of this one, subscribe. There is more where this came from. Slower, deeper, more detailed than most science content out there. Exactly the way I think this kind of subject deserves to be treated. And until next time, keep looking up. Part 11. When black holes eat stars, tidal disruption events. There is a particular kind of astronomical event that captures the most extreme version of what accretion looks like in real time. When a star wanders too close to a supermassive black hole, not close enough to cross the event horizon in one swift motion, but close enough that the tidal forces exceed the star's own self-gravity, the star is torn apart, stretched, shredded, and consumed. This process is called a tidal disruption event, and it represents one of the universe's most energetically vivid moments. Stars orbit in the outer regions of their host galaxies, far from the central black hole. Under ordinary circumstances, they are in stable orbits and will never venture close enough to the black hole to be disrupted. But over long timescales, gravitational interactions between stars in the dense central regions of galaxies can nudge individual stars onto highly elongated, plunging orbits that bring them close to the central, supermassive black hole. When a star arrives on such an orbit, and its closest approach distance is smaller than the tidal radius, the distance at which the black hole's tidal forces overwhelm the star's self-gravity, the star is disrupted. The tidal radius depends on both the mass of the black hole and the mass and radius of the star. For a sun-like star approaching a supermassive black hole of a few million solar masses like Sagittarius A star, disruption happens at a distance of a few tens of millions of kilometers. This is well outside the event horizon. The star is not swallowed whole. It is torn apart into a long, curving stream of stellar debris. About half of this debris is flung away from the black hole on unbound trajectories, escaping into space. The other half falls back toward the black hole, wrapping around and eventually settling into an accretion disk. As this newly formed disk accretes onto the black hole, it releases an enormous amount of energy, briefly lighting up the galactic nucleus in ultraviolet and X-ray radiation at a luminosity that can briefly match or exceed the combined output of all the stars in the galaxy. The light curve of a tidal disruption event has a characteristic shape. After the disruption, there is a rise as the fallback rate of stellar debris increases and accretion heats up. The flare peaks and then fades over weeks to months as the supply of infalling debris diminishes. At its peak, the luminosity can be extraordinary. Some tidal disruption events have been observed at luminosities of 10 to the 44 ergs per second, comparable to the brightest quasars. Astronomers are detecting more of these events than ever before, thanks to wide-field sky surveys that scan the entire sky repeatedly and flag sudden brightenings in galactic nuclei. Surveys like the Zwicky Transient Facility in California and the upcoming Rubin Observatory, which will survey the entire visible sky every 3 nights, are finding dozens of tidal disruption events per year. Each one is a window into the accretion process in real time, a chance to watch a black hole activate and brighten as it consumes what was once a star. Some tidal disruption events produce relativistic jets, powerful beams of energy launched perpendicular to the accretion disk at a significant fraction of the speed of light. These jets are detected as transient sources of radio and X-ray emission. When one of these jets happens to point toward Earth, the event is extraordinarily bright across multiple wavelengths. One such event, detected in 2011 and catalogued as Swift J 1644+57, was a tidal disruption event with a jet aligned with our line of sight. It was visible for months and provided an extraordinary opportunity to study jet formation in real time as a new accretion disk assembled around the black hole. There is something genuinely affecting about a tidal disruption event when you sit with it. A star that had been traveling through space for billions of years, burning its hydrogen, potentially hosting planets, part of the same galactic ecosystem as countless other stars, encounters the gravitational influence of the central black hole on an orbit that took perhaps millions of years to evolve into its final plunging shape. And then, in a matter of days, it is gone. Stretched into a stream, half of it flung outward into the galaxy, the other half spiraling inward to feed the darkness at the center. The star becomes an accretion disk. It briefly ignites the nucleus of its galaxy, and then fades as the consumed material runs out. The black hole is slightly heavier. The galaxy is slightly poorer by one star. And astronomers on a small planet, 27,000 light-years away, register a brief brightening in a distant galactic nucleus and know what happened. For Sagittarius A star specifically, tidal disruption events happen rarely, estimated at perhaps once every 10,000 to 100,000 years. There is an episode from the recent cosmic past that may be a remnant of exactly such an event. Observations of the gas cloud Scron B2, about 300 light-years from the galactic center, have shown patterns of X-ray fluorescence that look like echoes of a past outburst from Scron A star. The pattern suggests that Scron star was hundreds of times more luminous a few hundred years ago than it is today, likely due to a brief period of enhanced accretion. Was it a tidal disruption event? A particularly dense gas cloud falling in? The evidence suggests something dramatic happened in the galactic center within the last few hundred years, lighting up Scron A star brilliantly before it returned to its current quiescent state. Whatever happened, the light from that outburst has not yet reached the stars most distant from the galactic center. The echo is still traveling outward. In a sense, the event is still happening in the expanding shell of light, still moving through the galaxy. Part 12. Black holes and the lives of galaxies. One of the most profound shifts in our understanding of the universe over the past few decades has been the recognition that black holes and galaxies do not simply coexist. They shape each other. They evolve together. The supermassive black hole at the center of a galaxy is not a passive passenger inside its host. It is, in some sense, a co-author of the galaxy's story. This relationship became apparent through an observation that initially seemed like coincidence, but turned out to reflect something deep. The mass of a supermassive black hole correlates remarkably tightly with the properties of its host galaxy, particularly with the mass of the galaxy's central stellar bulge, and with the velocity dispersion of stars in the bulge. Larger, more massive galaxies have larger, more massive central black holes, and the ratio of black hole mass to galaxy mass is roughly constant across an enormous range of galaxy sizes and types. This is called the M-sigma relation, where M represents the black hole mass and sigma represents the stellar velocity dispersion of the bulge. The tightness of this correlation is striking, given that the black hole occupies a tiny volume at the very center of the galaxy, and that the stars whose velocity dispersion is being measured orbit at distances thousands of light-years from the black hole. The gravitational influence of the black hole cannot directly affect those stars, and yet their velocity dispersion is correlated with the black hole mass, as if the two had been calibrated against each other. The explanation is feedback. When a supermassive black hole is actively accreting large amounts of material and powering a luminous, active galactic nucleus, it is not just consuming matter. It is also releasing energy into its surroundings. This can happen in multiple ways. Radiation from the hot accretion disk can heat and ionize the surrounding gas, driving winds outward. The relativistic jets, launched by the most powerful active galactic nuclei, can blow enormous bubbles of hot gas through the surrounding medium, heating and pushing the gas that would otherwise fall inward and fuel both continued black hole growth and new star formation. This feedback is thought to be one of the primary regulators of galaxy growth. When a massive galaxy is still assembling, gas falls inward toward the center, fueling both star formation and the central black hole. As the black hole grows and its accretion rate increases, the energy it injects into the surrounding medium becomes significant. Eventually, the feedback heats the surrounding gas enough to shut off further accretion, both onto the black hole and in the regions where stars are forming. Star formation slows and stops. The galaxy transitions from an actively star-forming system to a more passive, quiescent state. This process, called AGN feedback, is invoked in models of galaxy formation to explain why the most massive galaxies are generally older, redder, and more stellar population rich than they should be if star formation had continued unchecked throughout their lifetimes. Without AGN feedback, simulations of galaxy formation produce galaxies that are far too massive, with far too many stars. Including the energy injection from central supermassive black holes produces a population of galaxies that matches observations far better. The jets launched by the most powerful AGN can extend far beyond the host galaxy. In galaxy clusters, where the central galaxy is often a massive elliptical sitting in a deep gravitational potential filled with hot X-ray emitting gas, the AGN jets of the central galaxy inflate enormous cavities in the X-ray emitting gas. These cavities, seen as dark bubbles in X-ray images of galaxy clusters, are regions from which the hot gas has been displaced by the expanding jets. They can extend for hundreds of thousands of light years. The energy stored in these bubbles is comparable to the total thermal energy of all the hot gas in the cluster core. The jets are not just decorative. They are a dominant heating mechanism for some of the largest structures in the universe. This raises a remarkable scale of influence. A supermassive black hole, billions of solar masses concentrated in a volume smaller than our solar system, influences the distribution and temperature of gas across a cluster of galaxies spanning millions of light years. The smallest scales of physics, the extreme physics of the innermost accretion disk, the magnetic fields near the event horizon, the jet launching mechanism, all of these connect through a chain of physical processes to the largest structures in the observable universe. The black hole is not isolated in the center of a galaxy. It is a nexus, an anchor point for processes that span a range of scales from the Schwarzschild radius outward to the edges of the observable universe. The early universe offers an even more extreme version of this relationship. Quasars, the most luminous active galactic nuclei, were far more common in the early universe than they are today. The peak of quasar activity occurred roughly 10 to 12 billion years ago, when the universe was much younger, denser, and richer in the cold gas needed to fuel rapid accretion. Some of these ancient quasars were powered by black holes of 10 billion solar masses or more, consuming matter at rates that challenge our models of how rapidly accretion can proceed. The discovery, using the James Webb Space Telescope, of massive black holes already in place within the first 500 million years after the Big Bang, suggests that supermassive black hole formation began extraordinarily early, possibly contemporaneously with the formation of the first galaxies. These objects challenge our current models of black hole seed formation and growth. They may require seed black holes of 10,000 solar masses or more, perhaps from the direct collapse of massive gas clouds, combined with extremely efficient accretion at the theoretical maximum rate or beyond. Understanding how these earliest monsters formed is a central challenge of observational and theoretical astrophysics in the current era of large space telescopes. The relationship between black holes and galaxies is thus not a static one. It is a dynamic, bidirectional conversation written in gas flows, radiation pressure, jet power, and gravitational potential. Black holes grow by consuming material that galaxy dynamics funnels toward them. Galaxies are shaped by the energy that growing black holes inject back into their environment. Each shapes the other. And the relationship extends back to the earliest times, when the universe was barely 1 billion years old and already producing some of the most massive black holes it will ever contain. Part 13. The Language of Spacetime: How We Detect the Invisible. Black holes, by definition, emit no light of their own. The event horizon is not a surface that reflects or emits radiation. The singularity is hidden behind the horizon. The region inside is causally disconnected from our observations. And yet we have detected black holes across a vast range of masses, distances, and environments. We have imaged 2 of them directly. We have measured the orbital dynamics of stars around the one at the center of our galaxy, and we have heard hundreds of them merge through ripples in space-time itself. How? The answer is that black holes are not invisible. They are not visible in the conventional sense of emitting light, but they announce themselves through their effects. And those effects, once you know what to look for, are written everywhere in the universe. The oldest and most indirect method is stellar dynamics. If you can observe stars or gas clouds in orbit around a compact, unseen central mass, you can infer the mass and size of that central object. This was how the mass of Sagittarius A star was established. The orbital dynamics of the stars, particularly S2, traced out an orbit with a period of about 16 years, a closest approach of 120 astronomical units, and velocities reaching 7,600 kilometers per second. No known physics other than a 4 to million solar mass black hole packed into a region smaller than those orbits could explain the observations. The Nobel Prize awarded to Genzel and Ghez in 2020 was for this work, the discovery, over decades of patient observation, of an invisible, compact, supermassive object at the center of our galaxy, identified solely through the motions of stars around it. Gravitational lensing is another approach. Massive objects curve space-time, and the curvature of space-time bends the paths of light rays passing nearby. A black hole on the line of sight between Earth and a distant star bends the light from that star, producing a characteristic brightening pattern as the black hole and star align. This is gravitational microlensing, and it has been used to identify black hole candidates in other star-forming regions, and even in the space between stars. The mass of a lensing object can be inferred from the duration and shape of the lensing event, combined with the stellar proper motions measured by astrometry. The first isolated black hole identified through microlensing was announced in 2022, a black hole with a mass of roughly 7 solar masses located about 5,000 light-years from Earth, revealed only by the subtle bending of background starlight. X-ray observations provide the most direct window into actively accreting black holes. The material spiraling inward through an accretion disk heats to temperatures of millions to hundreds of millions of degrees as it loses energy to viscosity and magnetic instabilities. At these temperatures, the thermal radiation is emitted primarily as X-rays. Black holes in binary star systems, where a companion star provides material for accretion, are among the brightest X-ray sources in the galaxy. The first black hole candidate ever identified, Cygnus 10-1, was detected as one of the first cosmic X-ray sources in the early days of X-ray astronomy, when rockets carrying X-ray detectors briefly lifted above Earth's atmosphere in the 1960s. Today, X-ray observatories including Chandra, XMM Newton, and the imaging X-ray Polarimetry Explorer have cataloged thousands of X-ray binary systems, many of them containing black holes. X-ray spectroscopy provides detailed information about the physical conditions close to the black hole. The iron K emission line at 6.4 kiloelectron volts, produced by fluorescence of iron atoms in the inner accretion disk when illuminated by corona X-rays, is broadened and skewed by the combination of Doppler shifts from the rapidly orbiting material and gravitational redshift from the proximity to the black hole. The shape of this distorted iron line encodes information about the spin of the black hole and the size of the innermost stable circular orbit. Measuring the iron line profiles of many black holes has provided one of the primary tools for measuring black hole spin statistically across a sample of systems. And then there is the gravitational wave channel, which we discussed in detail earlier, but which deserves recognition here in the context of the detection toolkit. Gravitational waves are not electromagnetic radiation. They are not particles. They are distortions of space-time geometry itself, propagating at the speed of light. They pass through all matter without significant interaction, which is simultaneously the reason they are so hard to detect and the reason they carry such pristine information from their sources. The LIGO-Virgo-Kagra network has transformed gravitational wave astronomy from a theoretical possibility to a routine observational tool, detecting hundreds of events and building up a catalog that is revealing the mass distribution, spin distribution, and merger rates of black hole populations across the observable universe. Each of these detection methods has its strengths and limitations. X-ray observations are powerful, but require active accretion and are limited by interstellar absorption. Stellar dynamics require bright stars in close orbits, limiting the technique to the galactic center and a handful of external galaxies with bright nuclear star clusters. Microlensing can find isolated black holes, but provides limited information and depends on alignment geometry. Gravitational waves are most sensitive to stellar mass mergers and are just beginning to probe the intermediate mass range. No single method is complete. Together, they provide complementary windows onto the black hole population of the universe. The Event Horizon Telescope represents something qualitatively different from all of these methods. Direct imaging of the shadow of the event horizon resolved at the angular scale of the black hole itself. This required assembling observations from across the Earth, processing petabytes of data, and applying sophisticated image reconstruction algorithms to produce images where every pixel represents information about the structure of the radio-emitting plasma within a few Schwarzschild radii of the event horizon. The result is a kind of seeing that was not imaginable in any practical sense even a few decades ago. A photograph not of the black hole itself, but of the darkness it carves into the glowing material around it. Future facilities will push further. The next generation Event Horizon Telescope, currently in planning stages, would add space-based telescopes to the array, providing even higher angular resolution and the ability to image more distant and more varied black holes. The Laser Interferometer Space Antenna, known as LISA, a gravitational wave detector being developed by the European Space Agency with deployment targeted for the mid-2030s, will detect gravitational waves from the mergers of supermassive black holes at the centers of merging galaxies, systems with total masses of millions to billions of solar masses. These events will produce gravitational wave signals lasting months to years, visible across most of the observable universe. LISA will essentially listen to the deepest bass notes of the universe's gravitational wave symphony, complementing the higher frequency detections of the ground-based LIGO network. There is something philosophically remarkable about all of this detection work. The universe contains objects defined by the impossibility of direct observation. Light cannot emerge from them. Signals cannot propagate out of them. And yet, through ingenuity, through the willingness to read the indirect signatures left in orbiting stars and accreting plasma and bent light and space-time ripples, humanity has managed to catalog hundreds of black holes, image the event horizon, shadow of the nearest supermassive examples, and detect the gravitational waves from their mergers in real time. We have not seen black holes directly. We have heard them, felt them, watched their influence on everything around them. And from those echoes and gravitational footprints, we have assembled a picture of the most extreme objects in the known universe that is, astonishingly, rich and detailed. Part 14. The Thermodynamics of the Abyss. One of the most striking intellectual leaps in the history of black hole physics was the recognition that black holes are not just massive objects described by geometry and gravity. They are thermodynamic systems. They have temperatures. They have entropy. They obey, in their own way, the laws of thermodynamics that govern the behavior of steam engines and refrigerators and every other physical system we have ever studied. This connection between black holes and thermodynamics was developed in the early 1970s by several physicists, most prominently Jacob Bekenstein, Stephen Hawking, Brandon Carter, and James Bardeen. It began with a mathematical observation. The laws of black hole mechanics, derived purely from general relativity, have a precise mathematical analog with the laws of thermodynamics. The 0th law of thermodynamics says that a system in thermal equilibrium has a constant temperature throughout. The corresponding law of black hole mechanics says that for a stationary black hole, the surface gravity, the gravitational acceleration at the event horizon, is the same everywhere on the horizon. Surface gravity plays the role of temperature. The first law of thermodynamics says that energy is conserved. The change in internal energy equals heat added minus work done. The corresponding black hole law says that when a black hole changes state, the changes in mass, area, angular momentum, and charge are related by a specific equation exactly analogous to the thermodynamic first law, with surface gravity playing the role of temperature and area playing the role of entropy. The second law of thermodynamics says that entropy never decreases in a closed system. Stephen Hawking proved a theorem in 1971, before his discovery of Hawking radiation, that the total area of black hole event horizons can never decrease in any physical process. Two black holes merging always produce a single black hole with area greater than the sum of the areas of the original two. This is called the area theorem, and it is the black hole analog of the second law. The third law of thermodynamics says that the entropy of a system approaches zero as its temperature approaches absolute zero. The corresponding black hole law says that the surface gravity of a black hole cannot be reduced to zero through any finite physical process. At first, these were viewed as a beautiful, but perhaps coincidental mathematical parallel, a structural resemblance between two different areas of physics rather than a deep connection. Bekenstein argued that the resemblance was not a coincidence, that the event horizon area literally is the entropy of the black hole, that black holes are thermodynamic systems. The entropy, he proposed, is proportional to the area of the event horizon measured in Planck areas, with each Planck area contributing 1 unit of entropy. This was initially resisted because if black holes have entropy, they must also have temperature, and if they have temperature, they must emit thermal radiation. But black holes cannot emit radiation. They are by definition regions from which nothing escapes. Then Hawking's 1974 calculation changed everything. Black holes do emit radiation. They have a real temperature. Bekenstein's identification of area with entropy was not just an analogy, but a literal truth. The entropy of a black hole is equal to 1/4 of its horizon area, measured in Planck units. This is the Bekenstein-Hawking entropy formula, and it is one of the most profound results in theoretical physics. What makes the Bekenstein-Hawking entropy so conceptually striking is how large it is. A stellar mass black hole of 10 solar masses has an entropy of roughly 10 to the 78 in dimensionless units. For comparison, the entropy of the Sun, an object of similar mass but without a black hole's extreme compactness, is roughly 10 to the 57. The black hole has about 10 to the 21 times more entropy than the Sunday. The black hole is almost incomprehensibly more disordered, or equivalently, its microscopic configuration is vastly more complex. This is where the connection to the information paradox becomes acute. Entropy, in statistical mechanics, is a count of the number of microscopic configurations consistent with the observed macroscopic properties. For a gas, the entropy reflects the number of ways you can arrange the atoms while keeping the total energy fixed. For a black hole, the Bekenstein-Hawking entropy says there should be roughly 10 to the 10 to the 78 different microscopic configurations, each giving the same macroscopic black hole of 10 solar masses. But according to the no-hair theorem of general relativity, all these configurations are indistinguishable from outside the black hole. What are these configurations? What is the microscopic description of black hole entropy? This question has driven an enormous amount of theoretical work. String theory has been able to count the microscopic states of certain highly symmetric, idealized black holes and reproduce the Bekenstein-Hawking entropy formula from first principles. This agreement, first achieved by Andrew Strominger and Qumran Vafa in 1996 for a specific class of extremal black holes, was a major triumph for string theory and provided some of the strongest evidence that the holographic principle is correct. The entropy is real, the microscopic states are real, and counting them from first principles gives the right answer. For more realistic astrophysical black holes, the microscopic counting is far less developed. But the theoretical framework suggests that the microscopic constituents of black hole entropy are quantum gravitational degrees of freedom living on the event horizon surface, consistent with the holographic picture in which the boundary of a region encodes all the information about its interior. The thermodynamic properties of black holes are not just theoretical curiosities, they are windows into the deepest structure of space-time. The fact that black holes have temperature, entropy, and obey thermodynamic laws is telling us that the event horizon is a physical surface with genuine microscopic structure, not a geometric abstraction. That structure is presumably quantum gravitational in nature, and understanding it fully will require the complete theory of quantum gravity that remains our most elusive theoretical prize. Part 15. Time, Infinity, and the Long Death of the Universe. Let us take a long view. Not the human view, or even the civilizational view, but the geological view, the cosmic view, the kind of view that puts humanity and Earth and the Sun and even the Milky Way in proper perspective as brief chapters in a story that extends far further than we usually allow ourselves to contemplate. Right now, in what cosmologists call the stelliferous era, The universe is filled with stars, hundreds of billions of galaxies, each containing hundreds of billions of stars. The sky is luminous with the light of burning hydrogen. Planets orbit those stars in countless systems. Some of those planets, in all likelihood, host life of some kind. The universe is, from a human perspective, brilliantly active. This era will not last. The rate of star formation across the universe has been declining for about 10 billion years. The peak was around 10 to 11 billion years ago. Since then, fewer and fewer new stars are born each year. The gas that fuels star formation is being consumed and locked up in stellar remnants. As the stelliferous era progresses, galaxies grow dimmer. New stars are born less and less frequently. Eventually, perhaps 100 trillion years from now, the last star will exhaust its fuel, expand, and fade. The universe will be dark in the usual sense. No more stellar fusion. No more nuclear burning. Just cooling stellar remnants, gas and dust clouds that never manage to collapse, black holes, and the background glow of Hawking radiation from the black holes themselves. This is the degenerate era. The universe is populated by white dwarfs, cooling slowly toward black dwarfs, by neutron stars spinning down as they radiate their rotational energy, and by black holes of every size sitting in the darkness. The stellar black holes formed in the stelliferous era persist. The supermassive black holes at galactic centers persist, growing slowly by swallowing the debris of their stellar populations. Eventually, on timescales that make the lifetime of stars seem momentary, even the white dwarfs and neutron stars fade. Protons may or may not decay. If they do, ordinary matter itself dissolves into lighter particles and radiation, leaving only black holes and the relics of dark matter. If protons do not decay, quantum tunneling processes will still, over incomprehensibly long timescales, convert ordinary matter into its lowest energy state, iron, 5, 6, and then eventually into black holes via rare quantum gravitational processes. What remains, eventually, is the black hole era. Black holes of all masses, floating in a universe approaching absolute zero, slowly radiating their mass away through Hawking radiation. The process is glacially slow. A black hole with the mass of the Sun would take roughly 10 to the 67 years to evaporate. The supermassive black holes at galactic centers, with masses of billions of solar masses, take roughly 10 to the 100 years. Numbers like this should produce vertigo. The current age of the universe is 13.8 billion years, which is about 10 to the 10 years. The evaporation time of a supermassive black hole is longer than the current age of the universe, by a factor so large that the current age of the universe is not even worth mentioning in comparison. But even these black holes will eventually evaporate. Their temperature rises as their mass decreases. Hawking radiation becomes more intense. The final stages are explosive. The last fraction of a solar mass radiates away in a burst of gamma rays and high-energy particles, and then nothing. The black hole is gone. An empty region of space-time where the most massive object in the late universe once sat. After all, the black holes have evaporated. What remains? Perhaps only radiation, photons from Hawking evaporation, particles emitted in the final bursts, traveling outward in an increasingly cold and empty universe. The photons redshift as the universe continues to expand. The temperature drops toward absolute zero asymptotically. The universe does not end with a bang or a crunch. It fades, it disperses. It approaches, perhaps but never quite reaches, a state of perfect thermodynamic equilibrium, maximum entropy, from which no further change is possible. Black holes are central characters in this ultimate act. They are the longest-lived complex objects in the universe. They outlast stars by unimaginable margins. They outlast white dwarfs and neutron stars. They outlast everything made of ordinary matter. For a window of time measured in 10 to the 100 years, the universe is a landscape of black holes and cold radiation, and the only physics of any consequence is the slow evaporation of those black holes by Hawking radiation, the gentlest drizzle of particles from objects that once marked the ends of stellar lives and the gravitational centers of entire galaxies. There is something almost peaceful about this picture, if you can hold it in mind, without being overwhelmed by the scales involved. The universe begins hot and dense, full of activity. It gradually cools and structures itself into galaxies and stars. Life appears in some of those structures, civilizations arise, and all the while, at the centers of galaxies, the black holes are quietly growing, accumulating mass, rearranging space-time in their vicinity. Then the stars die, the gas is consumed, the galaxies darken, and eventually, over timescales that make the current age of the universe look like the first morning of a very long life, even the black holes evaporate. The universe returns to simplicity, but not the hot, dense simplicity of the beginning. The cool, dispersed, utterly empty simplicity of an ending without a final moment, an entropy maximum that is approached forever but never quite completed. Black holes are not just the subject of this particular moment in science. They are, in a genuinely physical sense, the final chapter in the story of everything that has ever been made of matter, energy, and the curvature of space-time. Understanding them is not just an exercise in intellectual curiosity. It is an attempt to understand what the universe is, where it came from, and where it is going. It is an attempt to read the story from beginning to end, not just the chapter we happen to find ourselves in. And that, perhaps more than any specific fact about event horizons, or spaghettification, or Hawking radiation, or the Bekenstein-Hawking entropy, is why black holes matter. Not because they are dangerous or dramatic or dark, though they are all of those things, but because they are the universe's way of preserving, in one place, the most extreme version of everything physics is trying to understand. They are a question and an answer, a mystery and a laboratory, a beginning and an ending, all at once. The darkness at the center of the black hole is not empty. It is full of things we have not yet learned to see. A final word before you sleep. We have traveled a long way tonight, from the basic definition of a black hole to the deaths of massive stars that forge them, through the architecture of event horizons and singularities and photon spheres and accretion disks. We have sat with the experience of falling in and the strange split between what the infalling observer experiences and what the distant observer sees. We have visited Sagittarius A star at the center of our own galaxy, looked at the first image of its event horizon shadow, and understood a little of what it took to make that image possible. We have explored Hawking radiation, that almost impossibly gentle evaporation that will outlast every other physical process in the universe. We have sat with the information paradox and understood why it is not a peripheral problem, but a window into a fundamental incompatibility between our two greatest theories. We have listened to the gravitational wave signals of merging black holes and appreciated the extraordinary sensitivity required to detect the space-time tremors of events a billion light-years away. We have traced the deep relationship between black holes and the galaxies that host them, and the way that relationship shaped the universe across cosmic history. And we have asked the questions that cannot yet be answered. What is inside a black hole at its deepest level? What happens to information? What does quantum gravity look like at the singularity? Are there white holes? Are primordial black holes hiding in the dark matter? These questions are not embarrassments. They are the leading edge of the most exciting period of black hole science in human history. The universe keeps its most interesting secrets in the darkest places, and we are only just beginning to read them. If this video brought you something, whether it was wonder or peace or a sense of the scale of things, please consider sharing it with someone else who might feel the same way. And if you have questions, thoughts, things you want to explore in future videos, leave them in the comments. This channel exists because of people who find themselves up late, thinking about what the universe is made of and how it works. Like this video if it helped you see something more clearly. Subscribe if you want more of this kind of slow, deep science. And take your time tonight. The universe waited a very long time before you arrived to wonder about it. It is in no hurry. Good night.